of all, thanks for coming. I'm glad to be in your city. It's a beautiful city, by the way. I normally live in Krakow, so I'm quite happy to be here. So today I'll be talking about predictive analytics using neural networks. It will be around 50 to 60 minutes. I hope you will be patient enough. Just a quick check. How many of you don't know anything about neural networks? Okay, so there are some people who have no idea about neural networks. So I'll try to, for the rest of you guys, I will try to go through that point for a couple of minutes so that I hope it's not boring for you guys. About the rest of the thing, how many of you have heard about word2vec? Cool. And LSTM? And reinforcement learning. Cool. So that's quite a lot of audience who knows about it. That's always good. So the first thing, whenever I give a talk, I say, why am I giving this? And why are you guys here? Because it's quite important for me to have a reason to spend my time and you guys also. I think the reason I'm giving this talk is I often see that there is a gap between AI technology and AI application. People who write a lot about AI applications are often at a much higher level. Like AI will change the world and AI will change everything, but they don't go into specific things and how exactly that's being done. And then on the other side, you have very technical articles, which are often not understandable by majority of the people. So I'm trying to bridge the gap. And my goal here is at least have some of you tomorrow start building something in AI or using one of those algorithms that I have mentioned. So if I am able to achieve that, I will consider my talk to be successful. So first of all, I write about time series data. How many of you know what is a time series data? Cool. So in simple terms, it's a series of data over time, as simple as that. And you could see that any data could be seen as a time series data. Because most of the data that we have seen, whether it's an IoT, whether it's, in this case, Dow Jones or health data, it's always over a time and has a timestamp. So that's time series data. And many of you must have seen this. This is mixed panel, which is a screenshot from the mixed panel. And this shows what the user was doing over the last week or a month, where all he clicked, what all actions he did. Can someone tell me what exactly is missing in a mixed panel data or any of those analytics data that if you guys are using it? Anyone? Okay, I'll answer it. I heard people are not going to be so interactive, but okay. So the problem is that it's not predictive. What's the value of a data to see if it tells you about what the user did yesterday or day before yesterday? That has no value. What you really want to know is what the user is going to do tomorrow or day after tomorrow or in a week. And that's what is predictive analytics. So I will take one case study rather than taking 3 or 4 different applications. I will go into applications later on, but I will take one case study and dig on that particular case study and talk about how these 3 neural networks could be used to solve that problem. And the problem is, I want to predict what the next purchase will be of a user, which is quite a valuable information for many e-commerce websites or any company would like to know that. So I want to know what the next purchase of a customer is. This is a company called Instacart. Anyone have heard about this company? Okay. So Instacart, what they do, it's an online e-commerce. You can order groceries, but from a local store. And what it means that often people are ordering in real time. So if you want something in an hour or in 2 hours. And their unique USP is they will get order delivered within an hour. So you often have a real-time data, or sorry, an instant data of users, what their needs are at a given hour. So, as I said, that so for some of you who have not, most of you know about neural networks, some of you don't. So, in simple terms, a neural network will have some input layer, which has some nodes, which is an input. There are some hidden layers. You can see that input and hidden are connected via edges. There are weights, and and there is an output. So, and you propagate the value from the input to the output, and you will get a value in the output layer. I'll quickly go through some slides. For those who don't have an idea about that, I have a slide at the end, and I'll come back to this slide because I want you guys to really understand how does it done. So let's say is an example of a very simple neural network. You assign a weight of 0.5 to each edge. Your input is 0.10, and your expected output is 0.75. Once you propagate the value, your output you get 0.5, which is not the expected value. So you have an error, which is 0.25. Now something is called backpropagation. What you do is you adjust the weight so that you get the right value. So in this case, if you change the weight of the edge to 1.0, your output is 0.75. So it's a very simple way of understanding how neural networks work, how backpropagation works, and how does it train through backpropagation and adjust the weights. So you can imagine if you train this network over a lot of data, the weights will be adjusted so that you get the right output every time, right? Quite simple in a way. So coming back to so you all mostly understand what is a backpropagation, right? So the question is, how does neural networks can help make the prediction? So to that, we will be starting with something called a word-to-vec. That's a very simple neural network, which has one hidden layer. The inputs, the simplest form of this would be, let's say there are two versions of word-to-vec. I will take one of them so that I keep things simpler. Your input is, you have 4 words, so how are you feeling? And the output would be the next word of that sentence. As simple as that. So that's a neural network. And how does this work? That when you don't actually use, the network does not understand grammar or does not understand words. So it's not, you are not training it to understand a grammar. You're just training it to predict the next word of a sentence. How do you do that? So you start with some words in the input, and this is a training phase. Like as I showed you, so each word, let's say we represent with 0 and 1. So each word in your vocabulary represents one input node. Then what you do is you propagate the input through the network from the hidden input weights and from the hidden input weights to the output weights. And then you get an output, and you convert that output through something called a softmax. I will briefly explain that, which gives you an output in probabilities of a given word to be the next output. So your output will have all the words in the vocabulary, and the highest probability of the word will be the next output word. When you train, of course you don't know what is the word. Like as I showed you, you get the last word, and then you propagate back to get the right output. So you keep on training over hundreds and thousands or maybe millions of sentences, so that at the end, what you get is it learns the sentences. Now, basically, if you try to understand what is a neural network, it is approximation function. That's it. A neural network is an approximation function. So it tries to approximate how sentences are created based on our vocabulary or our sentences. We often create that. We will see patterns in that. So we have different patterns. So if you remember different patterns, you will know what will be the next output word. That's how we also work, and that's how neural networks is trying to approximate all the sentences that has been trained with. I use the word called semi-supervised, and this is something often people confuse. What is word2vec a semi-supervised or supervised learning? It is a semi-supervised because in a supervised learning, just for a bit more technical, is you're labeling the inputs. There is no label in a word2vec. You're just training it via backpropagation. So your words itself are the labels. So that's why it's a semi-supervised learning. But basically, it still learns through backpropagation. So you are training it with different sentences, trying to train it to learn those sentences, remember those sentences, and then when you actually give a real word or a sentence, it will keep that, it will give you the right output. Is that clear to anyone? I mean, anyone has a doubt? Did they understand the basic idea behind it? How does that work? Anyone has any questions, feel free to ask, because I just hope it's clear for you guys. I used a word called softmax function. Normally, I give you a very simple version of the neural network. Normally, your neural network output will have an activation function. The reason for that is you want to put your output between certain ranges. So you could use something called a semantic function. It's the most basic version, which gives you an output between 0 to 1. Then there is tanh, -1 to 1. And there are plus and minuses of each of those functions. The amount of learning. I'll not go into details of that, but softmax, as I said in word2vec, is a softmax, which is a multi-class regression, because a sigmoid is two-class regression. So it gives you a probability for two outputs. Now, when you have multiple words in the output, you want to have the probability across all those outputs. So it's a multi-class. And it's basically an extension from sigmoid. So just to understand that your output are all the words, so there are multiple words, and each of the words will get a probability of being the next word, and the word with the highest probability will be the next word. Now, that's basic way word2vec works, and that's how it basically predicts the next word in a given sentence. Now, how does that relate to predicting your next product that you will be ordering? There is something interesting that happens in word2vec, which even the people who made word2vec didn't know. And that's a very interesting feature that they found out later on. Let's look at this let's look at this graph where you have the input, you have one hidden node, and you have the output. The weights between the input and the output, you could define it in a matrix. And the weights between the hidden and the output could be defined as a matrix too. Your input from x1 to xv are these vocabulary, the different words. If your input is, let's say, one word, so only one of them will be 1 and the rest will be 0, right? So if you take only one of that as being the input, so the matrix that will be given by x dot wi, the matrix w1 and w dot, will represent something called a word embedding of that input word. Now the input word x, let's see if I want to know the word embedding of the xi word, then I will keep xi as 1, all the x1 to xv to be the rest as 0, and then I will calculate the value of x dot wi dot w0. And the x dot wi is like, it's a matrix like that, most of you perhaps know. So I'll give you a simple example, like say wi looks like something like that, w is some weights, and then if you're doing a word embedding of xi where you put xi as 0, the rest as 0, and you get a matrix. So that's your output will be matrix, and that represents the word embedding. Now what you could do, there's something called principal component analysis, again a statistical term, which converts that matrix. You can use that to convert. to a two-dimensional vector space. And what they have seen, that if you train the word to vec with different words and different sentences, and you plot that in a two-dimensional space, the words that appear in similar context, or which have similar semantics, occur in the similar groups, which you could kind of have an intuitive understanding, because it's basically when you're training a word to vec, you are training it to remember certain patterns, and you often will remember the words that occur in the sentence, and similar words occur in similar words occurring in the similar context often occur similarly. So your words in the city or words in the travel will occur together in a sentence. If you take multiple 10 different sentences, and if you use the word, let's say, places like Berlin and Paris and Bratislava occurring would be in the similar space. Basically, that's what it represents if you convert that into 2D space. Now that's part one. The part two is even more interesting, that not only that the words like countries appear in a similar space and the cities, but if you do a vectored distance between the Berlin, Germany, France, and Paris, you can do, and you will see that they are also equidistant. There is a very classic example like king, queen, man, woman. Or in this case, if you just ask, once you create this plot, if you ask Berlin minus Germany plus France, it will give you the answer Paris. So it shows that not only that the words in similar semantics appear similarly, but they are also kind of equidistant. It remembers the semantics in which the words appear in a sentence. So if you want to predict, now the prediction is even more interesting, because previously, using a word to vec, you can predict the next word in a given sentence. But now with word embeddings, you can actually even ask questions like, tell me, if the capital of Berlin, Germany is Berlin, what is the capital of France? And you just do a vector distance, calculate a distance, and you'll find the answer.
But does that apply to all of your data?
Yeah, that applies to all data. Even king, queen is the most classic example, that if you do king minus man plus queen, it will give a woman. That's how it works. And that's the feature that you could use to actually make the prediction. Now, coming back to our problem, that what we want to do, we want to predict the next order. Right? This is the data that actually Instacart have made it online. They have created around 3.2 million orders that they had prior. There was a training data, and actually Instacart uses word to vec to create the recommendation list. And I'm just showing one of the tables from the data. And you can see there's, of course, the user ID is anonymized. But you have order number, date of DOW that stands for date of the week, which is one is, I think, Sunday, hour of the day, and date price. So it's basically they have the data that they're using, and then they're using that to train a word to vec. Where inputs you give products, and you train it that what is the next product. Because when you order, if you see again intuitively, when we order online or even when you go to shop, we often try to do the similar patterns. We remember the same pattern. We order the same things together. So if once you train the word to vec, you could actually, when you plot that graph, then drinks will come together and the snacks, let's say, will come together. And if someone has ordered product 1 and 2 and 4, you would perhaps know the next order of the guy would be 3. Is that clear? That makes sense for most of you? Anyone else? Okay. Yeah, sure.
Sorry, I have one question. So, on the previous slide, you showed that the input of the network is basically just the product IDs, the output as well. So, what about the rest of the data that is available, like the hour of the day?
I'll come back to that.
Okay.
Thanks for asking that question. I just want to show you that although what I explained word2vec how it works, you don't really have to know how it works, but I think it's always good to know before you use it. So there is an in TensorFlow, there is a library, and there is a function called feed_date. All you could do is you can feed the word2vec with the data you have, and it will train. So, but again, I think that for any programmer should understand how the basic things work, so you don't really need, but you don't have to understand. But this is now, if you want to apply this in different problems, you can think about so many problems that you could potentially use on to predict something. The basic thing word2vec applies on the principle we humans have a repeated patterns. So our actions are repeated. If you could think of a case where you could have some data, which is where humans are repeating over and over action, you can use word2vec to predict the next action. Just wanted to ask you guys, anyone have any use case on this? Can anyone have anything which they think could be used word2vec for? Okay, yeah, sure.
Like when to buy the next toilet paper, for example.
Well, it could be any product, that's true. But you could, think about the next, like that's one use case of predicting the next product. But it could be something, which city you might want to go next. Like travel startups could use that. Like based on your previous places you have been, what is the most likely place you would be going? Yeah.
Do they offer discount for those items which are supposed to be?
Well, you can do that. I mean, that's again a way to incentivize, and that's a way to make people sell. So you could add things on that. But the basic bottom line is, if you know what the person is going to order, you can create so many interesting features on that and sell a lot more. Now, what is missing? As you pointed out rightly, what is missing is
Sequence.
yes. But we ordered a sequence. Exactly. This is a graph also from Instagram. And they showed that when people order, the green is normally the more healthy products and the red are more unhealthy products. People normally tend to order healthy products in the day, and as the day progresses towards the evening, they're more ordering unhealthy products. And the bottom line, basically, which what I want to show that the sequence of order is important. word2vec doesn't keep that sequence, like which day, when, which month you are ordering. The things that you're ordering in November is not those things you might be ordering in April. So you would like to train a network which also remembers the sequence of your order. As I said out that you have the data, or people have the data. So there is a class of neural networks called recurrent neural networks, RNN, which successive neural networks are joined together. And this, in a way, remembers. So it's a memory. So you can add one network, then the next input is the next time, the third input is the third time, the fourth input is the fourth time. So that's a broad class of networks. However, they suffer from something called the vanishing gradient problem, which is also a problem many neural networks face, but I showed you how backpropagation works, right? So if you want to train a network, you go and adjust the weights backwards. Now imagine if your network has 50 neural networks in between. The backpropagation, when it works, it tends to train the networks towards the end more and less towards in the beginning. Because as you are adjusting the weights, you'll most likely adjust the weights towards E3 and E4 rather than the ones in the beginning. And that's called a vanishing gradient problem. And that also is a neural network, but it's more in RNN. So LSTM actually solves that. So LSTM is a type of RNN. You have multiple net cells. So each A and those represents each cell. I'll not say neural network because it's more complicated than just a neural network. So, and there are four basic things that I will try to explain how it works. Something called gates. I'll come back to that. And something called a cell state. You see the line that goes on the top. This connects between different cells. That's called a cell state, and that acts as the memory. So you pass on the information from one cell to the other cell to the cell state. That's number one. So it kind of remembers data from the previous network, rather than just successively adding few neural networks. And it has three types of neural networks inside that one cell. Well, there are actually four. You could see there are the yellow ones. Each of them are a neural network. I will not go in details, but just briefly, the signs that you see, the three of those are sigmoid functions. So they use activation and sigmoid function, and this one is tangent. So remember I was showing you about the activation functions in neural network. So these are four different neural networks. Three of them use a sigmoid function, one uses tangent function. But I don't think that's too much to need to understand, but I'll try to explain how does this work at a bit higher level. So as I said, there are these activation functions. Now, there are three gates. The structure of each cell could be divided into three gates. The first gate is a forget gate. And that trains the neural network what to forget. The second is an input gate. What it does, it trains what to update and trains the update state. And then what you do, you see the cross and the plus. So the cross is forgetting. So the forget gate forgets something from the cell state. That comes from the previous cell. And then the next input gate adds something into the cell state. So it's being explicitly done. And then there is an output gate, which this neural network goes into a tangent and then it goes an output. Again, I will not go into details of each of those. That's not important. But important thing is to perhaps at an intermediate level understand that each LSTM is divided into three main gates, and each of those gates performs an action so that it updates the cell state and gives an output. I'll give you. So, for example, if you have to, let's say the example of the product basket that we had. Let's say you have a list of future products as a input to this cell. And the input of this cell is a product that the user selects. Now, based on the new selection, you might want to remove something from that basket that may not be any more relevant. You might want to update or add something new, which is a future recommendation. And you want to output that is the most likely the next order, not just the list of order, but the next exact what would be the next order. So you could train a cell to perform that. Is that understandable, that how LSTM works and how you could train multiple cells to perform an action? Yeah.
Just one question, the list of future products, isn't that a black box from the point of view of the user?
For the user, yes.
Yes.
The user would not know.
He doesn't understand the...
He doesn't have to understand, absolutely.
Okay. No, I don't mean the user, but I mean the human who is looking at the output. Is it a list of products or is it...
Let's say, yeah, you want to show, let's say someone is, you want to see a list of products as a recommendation, what he should buy next.
Mm-hmm.
And you want the output of this is the exact, the next order should be the first one we should buy.
Okay.
I didn't know that, but I actually saw that Zalando, I guess many of you know, it's a big e-commerce company, they use LSTM network also. And this has been in one blog they have posted in a very discreet way, have put some pictures, not really explaining anything much. But what they are doing also is they're training an LSTM network based on the user actions. So the user at 8:23 click, there's an RN. When say RNN, it's an LSTM, it's not an RNN. I can tell you that. They didn't say that, but that's another thing. So even big e-commerce companies are using or looking into using LSTM to predict the next product that someone will order. Now imagine what can that do. These are the two articles that came out in 2017. Amazon wants to know what you want to buy before you buy it. Again, a very high level saying what they are doing, nothing, no technical details. And Walmart wants to know when your milk is about to expire. Walmart is saying that before even you go and order anything, they will send you the milk to your home. And it's not a rocket science, it's something that they're going to do, I think, this year already. So they are going to use LSTM networks and things like that. Again, you don't have to build the LSTM network. There are APIs. TensorFlow provides you the APIs. You just have to call the APIs appropriately. Once you understand how these networks work, you could potentially now write a piece of code, a Python program often, when calling the right APIs in LSTM and train an LSTM based on the data that you hopefully have. So what is the use case of LSTM is where you have repeated patterns of human actions, like in word2vec, but done over a longer duration of time. So things that you are doing, for years or maybe 2 years, and things that it wants to remember from your past, like a year or 2 years ago. I will let you guys think about if you have any use cases, but I'm pretty sure you guys could think about so many use cases that people do.
Is that used for Netflix, for example?
I don't know what Netflix uses, but you can potentially use it for Netflix also, yes. Anything that you're ordering online that you have ordered in the past, you could use LSTM or you could use
Predictions of next films.
Yes.
Suggestions.
Now, what is missing in these? Can anyone think about what was missing in either LSTM or word2vec? Or if I ask you guys, can you go and build something using LSTM or word2vec? Do you think you can do that?
Yes.
How would you do that? Tell me.
You use TensorFlow.
No, but you have to have data.
Yeah.
You have the data?
No. Yes.
Okay, that's good for you. Most of us don't have a data, right? That's why, I know it's being recorded, that's why a lot of companies like Google and they are letting people use the LSTMs and word2vecs because they know that without the data, you cannot do much about it. And they know they have the data. So they say, okay, go and use it, but okay, I have the data, so that's the problem. That most people don't have data. Those that you are facing day to day may not have data. I mean, many companies have, like banks and things, but many of us don't. So that's the problem, that there is no data. So there comes something called reinforcement learning. Although I will say that I'm exploring this in the context of the product, but this is being used and has been used very well in different problems. For example, how many of you know what is an AlphaGo? Okay, so AlphaGo kind of uses reinforcement learning. It uses to build intuition. Self-driving cars is being trained using reinforcement learning because you cannot have data of self-driving cars. You don't have the data. So what it does, and I will not go into too much details of that, also because I think is already have explained a few things, but I will explain one of those algorithms. How does it work? So basic idea of reinforcement learning is there's an agent that makes an action in a real world. That's the environment. There's just change of state because of the action, and the agent gets some reward. As simple as that. So, and then the agent learns what actions it will do, and it gets the best reward. Actually, that's how we learn. When a child learns, if you give him something, he does something, and so take that, I did a good job. So they keep on repeating. That's how human learns. So reinforcement learning is basically imitating how humans learn. So one of the algorithms, there are two algorithms basically of reinforcement learning. One is called Q learning. So what you do is there's a reward function for each action. So you provide an action, you assign a reward function. And then you calculate something called a Q value. The Q value from a state with an action is equal to the reward of the state and the action plus a lambda function, which is a fixed variable, with all the future Q states with states and actions. I'll give an example so that you guys could understand it. And you initially start with a Q value of 0. And the value that you assign to the lambda varies between 0 and 1 depending on how far you want the agent to learn. So if you see that the lambda is of high value, then it will assign the future actions more than the present action. So it will try to learn more from the future than the present. So your lambda normally depends on how far you want the agent to learn from. I took this example from the web. I've given the link here. So I'll explain that how a Q learning works. So let's say the problem is you are in the start state of 2, that's a house, and you want to go to the finished state of 5. You can represent as a graph and you assign rewards. So the only reward that you get is when you reach to your final state, which is 100, and the rest are 0. That's the reward matrix. So I'm explaining this in a basic version, and then later on I'll explain how can that be done in neural network. But that's the reward function. And then if you just go to the calculations, you calculate the Q matrix. For example, in the Q 3 to 1, if you are in the Q value of 3 to 1, the third state and doing an action 1, if you do the calculation, you will come with 400. So, and you can do the calculation to create the Q matrix. Now, once you create the Q matrix, this is done like, let's say, to a program done in programming you're using it. For now, there is no neural networks, right? Sir? Let's say you're in the state 2. So you can see that you pick the highest Q value, the action that has the highest Q value, which is 3. So it does an action to move to 3. Now once you're in the state 3, you pick the one with the highest Q value. Let's say to the 1. Then you move to the state 1. Then you select the one with the highest Q value, is 500, which goes to state 5. So it learns through a Q value to create an action to reach to the state 5. And once you're in the 5, you keep on staying in the 5 because that's where your highest Q value is. So in a very simple way, you train an agent through Q values and rewards to create an action to reach from a start to end state. Now you could actually, since we said that any neural network is an approximation function, you can train a neural network to exactly imitate this function that we made. You did this in hand or mathematically to program. But you can have a state as 0, all the states you can write, and you can output as a Q values. Your error function, which is a loss function, the error function will be a sigma of Q target I, which is, the Q target I is basically this function that we wrote it down. And then you train the neural network based on what is the current Q. So you start with a Q all being 0, and you get the output, all your weights are 0, you start, and then you keep on propagating the value, and you can train the neural network to imitate the function that you have done in the previous exercise. However, the problem here is that you have this Q value for the actions, right? The next algorithm is called policy gradient, where you are not training the Q value, you're actually training on the action space itself. So your output of the neural network is not the Q value, but it's actually the different actions and the probabilities of different actions. And this is being used in most reinforcement learning. There are mathematical proofs that why this is better over other, but often if your action space is continuous action space, So it's not like discrete action spaces. You would use a policy gradient rather than a Q-value. But that's basic idea of how reinforcement learning works through training and the real data. So you do something, see the action, and provide an feedback, and keep on training that. So potentially, if you have to train the products that you want to use, like feature prediction, you can use something like each of those as being through the reinforcement learning. So your input is a product, you train it, keep on training, and your output is a product is actually based on the real action of the user rather than on the action or data that you have. However, the problem here is that you need a lot of user actions and a lot of where people will not be happy. So that's the problem with this. But that's one way you could train a reinforcement learning to if you don't have the data, to train a network to predict the next one. I'll play a video, which I think is quite exciting, to see how reinforcement learning can train. And this is using policy gradient. So they start with the initial policy, and they just, you see that it's not able to play, so it keeps on training. And it gets reward. Every time it does something good, it gets a reward. So it starts learning how to hit the ball. And now you see, slowly it's end up playing really well. So you could, a lot of robots, robotic arms, self-driving cars are using policy gradient. Again, I think there was a slide on, you don't have to train, you don't have to build this algorithm. TensorFlow also has libraries of reinforcement learning. But you have to implement on a given use case. So you have to take a use case, write a piece of code which interfaces with the TensorFlow library, and you can start training something. So the use case for reinforcement learning is where you cannot get a past data. Like how do you train a robot to train? You don't have any past data. Oh yeah, this is the TensorFlow reinforce. That's a library. I mean, I'm not going into details of each of these functions that are available, but that anyone can go into the site and read those. I think I wanted to give you guys an overall understanding of how these different algorithms work and how could you implement them in just if I take a simple case of predicting the next order. Now, that's one use case that I said. I'm sure you guys could think about a lot of use cases. One of the most important use cases that I've heard, I was in Vietnam last month, and I was told that 80% of people in Vietnam don't have bank accounts. Now, if they want to take a loan, they cannot take a loan because there is no record. How do you predict someone is going to default a loan or not without having any data about the person? That's an open problem. Some companies are solving it, but it's a billion-dollar problem if someone can solve it. There are companies I know I think I spoke with some company in, about the country, sorry, but they are solving this problem. But that's basically giving credit scores to people based on their certain behaviors, not behavior of what their bank account statements is. This is a company I was one of the founding member of, insurance sector. What we did, the young people, when they start cars driving, their premiums are very high because insurance companies do not know how to give the right premium for you. So they just see a record in the past 10 years and they say, okay, you're a good driver or a bad driver. But when someone is starting, there is no way. So their premiums are very high. What we did is we collected data of how someone is driving today, yesterday, day before yesterday. And then we gamified the whole system. we learn how people are driving. And we wanted to predict who is likely to be in an accident in a year or so. What we saw, that it's not only that your driving data that says how likely you are going to be in an accident in future, but your social data also matters. For example, if you are a bad driver, but your friends are a good driver, then you are most likely will not be in an accident. But if you're a bad driver, equally bad as that other guy, but your friends are also a bad driver, most likely you will have a high chance of being in an accident. So if you combine, yeah, sure.
I just wanted to ask, how can you separate causality and correlation?
How can you separate the causality with correlation? But we are not trying to separate the causality, right? We are not saying that this would mean that. We are just trying to predict the probability of someone being in an accident. We are not trying to find a reason behind that accident. We are not saying...
Yeah, but the probability, I guess, prediction is based on correlation rather
Yes.
than on causality.
Yeah. It could be a causality also, but for us, doesn't matter, right? Because we want to just predict the reason. We are not trying to find a reason behind it. So if we want to find a reason, then we want to know whether it's a causality or a correlation.
Yes.
But we are not trying to understand the reason behind it. We're just trying to predict the probability.
Belgium?
Yes. I had a company in Belgium. You work with KBC, insurance companies. Healthcare is another huge sector. If I could predict when are you planning to have your next, I don't know, heart attack or sickness, a huge value. You could take any sector, and if you apply predictive analytics on that sector, you could provide a value 5 to 10 times more. Many of you think why people don't do that. Well, first of all, it's not so easy. Of course not, but it is possible. It's not that difficult either. But often I was talking to someone who is working or has connection with banks, not only here but around the world, and they said the banks don't know how to do it. They lack people who understand these technologies, they understand this. But if someone could come to them and say, hey, I could help you understand your data and do some predictions, they would love that. So many of you, if you want to explore this sector, talk to a big company, say, hey, I can help you build the systems. And I think that would be huge value for many of those companies. You can take any sector, as I said, and if you apply predictions on the data, either what they have, a huge value. Now, I explained different algorithms. I explained how you could use potentially neural networks work and how could you use them to do some predictions. But what are the pitfalls? Can someone tell me what do you think is one of the problems of using such kind of network or such kind of neural networks?
You could easily overfit.
Well, that's a problem with the neural network itself, right? You can overfit the network. So, but that's not the problem of the algorithm itself. You could train the network to not overfit also, right? But I'm not talking about the problem of neural networks, but I'm saying overall using neural networks to solve these kind of problems. Like, because AI is much bigger than a machine learning or neural networks. You could think about what problems are there of using neural networks, of solving the problems.
Maybe a training time.
Sorry?
Training time.
One of the problems is training time, one is the problem of data. I'm still going on one more level.
For example, if you have like two indistinguishable probabilities, like for example, you have the data where you have the healthy products and the unhealthy products, and okay, you said that after a certain hour, people are more probable to buy unhealthy, but the unhealthy and the healthy products were quite close in the probability terms. So probably distinguishing between these kind of cases might be a problem if the probability is very similar for two opposite choices.
Okay, I can say that. I was actually coming to something which was, you said actually. You said about distinction between a causality and correlation, and I told you that I was not trying to find a reason behind it, right?
Yeah.
And that is the biggest pitfall of using neural networks. Anyone knows what is a trolley problem? It's a philosophical problem. I'll give you the problem and you guys can think of it. The problem is there's a trolley that's going. If it goes straight, it's supposed to go straight. There are 4 people it will kill because they are on the rails. But the guy with the lever, if he changes, the trolley will move to the right, but it will kill 1 person. What should the guy with the lever do?
Stop.
That's not an option.
Blame it on an AI.
I'm sorry?
You should consult an AI and blame it on that.
Well, I don't know, I mean, that's a dilemma. So I was saying this is you can go and talk about it for hours and there's a whole philosophical behind it. And there is no right and wrong answer. What I wanted to say here, imagine instead of the guy, it's an AI machine. If, let's just a self-driving car. It's a machine that makes a decision rather than the human. How does the machine will make a decision? On what basis?
Probability.
But probability based on what? What is the logic? You know, it doesn't train itself by killing 4 people and 1 people.
Well, but you have this dilemma when you have like humanitarian missions and they have to decide like 2 people. So, okay, am I going to save this guy who can be saved, or am I going to let this guy die because I know he's going to die?
I understand, but that's human makes the decision. How does the machine you train, on what data you will train? Who will train? Where is the data? How do you train? What is the logic that you will apply?
You get their Facebook account.
I'm sorry, I can't hear you.
You can get their Facebook accounts and decide on that.
And then check what? Who is young? Kill the old people and keep the young? Who is not capping? But anyway, what I'm trying to come to is that AI systems, neural networks, doesn't give you the it gives you the output, but you cannot. Doesn't store the reason, the provenance of an action. Why did it do that? And even the top neural network experts and machine learning, they say it's a black box. You train with data, it trains with the data, it adjusts the weight somehow, and you get an output, which might be the right output. But you would not know why this output came. Where is the connection between this and the previous, any of those data that was being trained with? That's okay with when you are doing something like checking an image between a cat and a cow or what's there. But if it comes to decisions about life and death, you want the machine to know what it is. There was a paper that came up last year called Ethically Aligned Design, and they said that the whole current approach of using machine learnings should change because you want machines to always be able to show the process which led to their actions. Current algorithms, especially neural networks, is not able to do that.
Humans aren't capable either. So.
Absolutely. But the goal here is to make machines which are perhaps better than us, right? That's why we are making machines. And why do we want to have machines and just have humans? So if there is, so they came up with basically that you want to be machines to be transparent, accountable, and minimize the risk of being misused. And fair enough. But the current algorithms don't do that. None of those. They're not transparent. They're not accountable. And you don't know how they'll misuse or not. So that gives an open question. And there are people in the States mostly who are looking at the AI as a completely different way than how, you know, the whole neural network community and their sort of, they are basically completely secretive, so they don't tell what they're doing, but that's the problem. So thanks for listening. I hope it was interesting for you guys, and I'm happy to take questions if you have. Anyone has questions? Yeah. Shall I give the mic to you? I can come to you. What do you want to
Just ask.
Yeah.
So you explained the word vector framework, but you actually didn't use it to solve any of those problems, or did I miss something about it? Or?
Yeah, no, I did explain that how can you use that for the, once you create the word embeddings and you know the vector distance, you could train the word to vec with products, and then you can apply that
Okay.
to predict the next product, right?
Yeah, okay, so it was like a simpler example, but I expected that you would somehow combine them to create a better representation of the products and then to feed them to the vector. And
No, it's not a better representation. What you do is once you train the word2vec with your history of products, it will create the word embeddings, right? Once you have the word embeddings, you can easily just do a like vector addition and subtraction to predict the next product. So I didn't go in that details, but you understand that's, to me, was like I give a high level explanation, but that's based on the word embedding that's being created. If you do information, you need an environment. Do you let the agent to interact with the actual users? Well, I think that to be honest, I'll just accept it. I'm not sure of the answer to this question, to be honest. Now, whether you would let the user to actual user or not, I think depends on the case. Sometimes you might want to do that. Sometimes you might not want to do that. So it's more of the based on the cases. I'm thinking in which cases you want them to do that, in which cases you don't. I showed you the example of the playing ping pong, right? In that case, you do definitely want them to directly interact with the agent and get the feedback. But in some cases, you might want to do some control. I'm just thinking in a self-driving car, if you want to train, do you want to do the interact with the actual users? Maybe not. That's part I'm not sure, but in many cases, you want it to do the directly with the agent. So it depends on the cases. To me, it seems as long as you are not making a risk to the user, it should be fine. Yes, it is still operational. We actually partly sold it to a research lab in Belgium who are running it. And yes, I left the company a year and a half ago.
So do they base the insurance expenses based on your system?
So the insurance companies are very slow movers. So they still don't want to do that. But what they do use it is to create a user engagement. So what it does is, one of the problems that insurance companies have, they don't have an active user. So people don't take insurance because they love it. They take insurance because they hate it. They just have to take it. So what they use our systems mostly is to create a community who are actively using the app, providing the data, and we gamify the whole system. So it's create more of a brand. The reason the insurance companies said they don't do that is because they're actuaries and they're too sophisticated to just change, disrupt suddenly. That's the reason they don't do it. But there are companies I know who don't provide the exact details, but it provides some discount. So for example, if they see that you have a low risk, they will give you a discount. They will not say that, okay, you are low risk, but they will show the discount. I'm sorry, there was a question that went away, the Bitcoin.
This one is there.
Okay, do you have your AI? What's the score? Do you have your AI Bitcoin bot already? No, I don't have. What's the biggest pitfall you expect in the time trade prediction? But trading is one of the first applications of AI. Way back in 2003, when I first started, 2002, I remember even 2004, they were using kind of different types of tree search and not neural networks to do the prediction. So what is the biggest pitfall you expect? Because I don't see this in, trading is not a decision about making lives, right? It's not like, unless it changes people's life. But normally, I think the pitfall are more into things which are about whether they will give you a credit or not, or whether your insurance matters or not. I think trading is anyway a risky proposition, and people who go into trading know it's a risk. So even if your AI is giving you the wrong answers, people take into knowledge that yes, there is a risk involved in that. So I don't see any big pitfall, and I think trading is one of the most common use of prediction, and not now, it's used for the last 15 years, I think at least, where they've been using AI algorithms. Simple ones like tree search in the past, but to predict what ML problem. So I've been working on one thing which is called, I wrote an article a week ago, understanding human behavior. So I read a book a month ago, which says that humans do not behave according to economic models. To give you one example from the book, really good. It's written by a guy who won a Nobel Prize in economics last year. Imagine you bought a wine bottle for $15, and now you know the price of the bottle is $70, and you are drinking the wine bottle or that wine. How would you price that bottle? So you know you bought for 15, but now it's $70 it costs, and you are drinking that wine. How much will you cost? What would you assign the cost of that wine bottle that you are drinking now? 15? But you know it's cost now 70.
70 minus 15.
The profit. Anyway, I mean, yes, again, and most people answered 0. Because they say, I already bought it. But when the question flipped and asked, you broke that bottle instead of drinking it. What is the cost, opportunity, lost cost, sunk cost for you? What did you answer then? Which is? 35? 70, exactly. Most people answer 70. Doesn't make sense. I give you the example just to show that humans don't behave by economic models. So it's very hard. No economic model, no model have been built to predict human behavior. So what I'm trying to understand is, can we use machine learning algorithms on a given context? Let's say, what are you going to, in the example I gave you, what are you going to order next? But can I predict who is the next person who is going to buy something new? So you have never bought anything, and I want to know, you are more likely to buy something in a week or in a month. And imagine if I can know that, companies would love that, because company can know exactly that you are going to buy something in a month. And now I can call and say, hey, you're planning to think of buying something. So that's a problem that I'm checking. I wrote one article about it, so you can go and check it also. But what most companies, the so-called AI or so-called, they do is data mining. They go to the internet and they see what people are writing. So if imagine you go to a LinkedIn post and say, hey, I'm looking for developers. And then they just mine the data and they say, okay, this is the guy who is going to buy. But that's already too late for someone. So I'm trying to predict even before that, based on the needs. So that's what I'm working on. Are you a proponent of symbolic AI? Actually, I haven't even thought about it. So,
maybe I can explain the question.
Yes.
If you say that there's a problem in the fact that it's a black box, then what do you want? I mean, you want symbols you can see where you can.
You want a record of what makes the output. How do you know that this output? Why is that decision was made? So you can show that the decision of this was, the reason behind making the decision was this, and this. These are the 5 things you did that made me decide, or that machine decided that you are more likely to be an accident. That's what most people in the AI community want that.
Why?
Because if tomorrow, imagine yourself, you come to a bank and the bank says, I cannot give you a loan because of something. And you say, why? You want to know why, right? So then the bank should be able to tell you that why I am not giving you the bank loan. So the provenance of an action is very important. Or if tomorrow government makes decisions based on an AI machine, the AI says, most likely create a policy to help this many people. You want to know why is this policy made? What was the reason behind making the policy? Any effective ways to obfuscate the learning and or rewarding process from the point of end user, meaning I want to top up my score? I'm sorry, I'm not getting the question. Can someone explain it? What is the question?
Yes, so if there are any ways to trick the system into people in China are getting scores for different kind of things based on similar processes, for example. So if there is any kind of activity, maybe not individual, but group activity that can influence such decision-making machine.
So, if I'm right, what you are trying to say is that you can create different groups of people and their behavior patterns are different, and then you can train neural networks on those people.
Yeah,
absolutely.
like a community will decide that
absolutely
we want to see into this.
Yeah. So that's one of the problems I'm also checking is a few months ago I wrote something about how different cultures, people behave differently. So I compared 5 countries where I have built companies, US, UK, Belgium, Poland and India. And I show that people in these different countries behave differently in terms of how they make decisions, how they trust people, how they communicate with people. One simple example I'll tell you. For example, how to say no. I don't know how it is in here, but Indians normally don't know how to say no. So if you ask a question, they will never say no. They will just keep on answering something. It's completely different in UK. So there are different cultural differences. And human behavior depends on that. So you can potentially train different networks based on the different groups that you have created. So you have to make certain assumptions in the beginning. So the problem of neural networks is it as good as your data is? So if you train with the wrong data, you just get a completely different output. So yes, you should make those. Successfully solved. Successfully solved. I think that's a difficult question. I think perhaps doing some playing games or something. I don't think I have solved any real problem which is successfully solved. Because success, if I haven't built any chatbots, I don't think that's a problem that I want to solve. Or image recognition. I'm more interested in solving problems of predictions using perhaps human behaviors, which I haven't successfully solved. So if that answers the question. And I don't think anyone have till now done that actually. I think it's a problem that, there is, I don't think there's any, someone can say I've successfully do predictions well. The best, even in AI, the best solution is AlphaGo, which has been able to build an intuition to play the game of Go. I think that's the biggest success of AI till now. And it defeated Lee Sedol twice. So Lee Sedol is the #1 in Go. I guess you guys know about the Go game because it's a very intuition-based rather than rule-based. So that's the biggest success of AI. So you can imagine the biggest success of AI all over the world is making a machine which plays Go. So yeah, that would answer your question perhaps about mind solving problems. There are a lot actually. It's very hard to say that. I mean, if you go into ML, I have some references in the slides, but there's a lot of text out there. There's a lot of people have written. I don't think there's one article. I mean, I can send you a list. I mean, whoever asked me the question, feel free to send me an email, and I can send you the list of articles that I think are very good on this case. But I don't think it's human readable. By the way, what is human readable? You mean non-technical or technical?
No text my own, just reading article by
Oh, but that's not human readable, that's human created. Okay, I thought that human readable is perhaps, you want to talk about non-technical or technical. I think everything is human readable, so. Do you think future machines algorithms will be able to perfectly predict future behavior? I hope so. I mean, that's something I think even in the you have to take context. It's very hard to create a generic machine, AI machine. I don't think that's something where even 20 years behind it. But if you're taking a given context, like your next order, take a problem or next buying thing. What are you going to buy next? I think next order is something that Amazon, they are doing it well. I think they should be, and I think you could do certain human behavior predict.
What about rather influencing than predicting?
But that's a philosophical question in a way, right?
Like they give you a suggestion and you wouldn't do that, but you will because they give you the suggestion.
Yeah, but for that you don't need an. Yeah, I just said it's a philosophical question, and where do you what humans are actually doing? Is it because they showed something, or they actually were planning to do that? I don't know. That's a philosophical question. I don't think it's an AI-related question more about. It's more philosophical. Yeah. Cool. Yeah.
Why is that Python became the most used language for this?
Because Python has background in mathematics. There's a lot of good libraries in mathematics, mathematical libraries. Python has. That's why Python is used more extensively in machine learning, because of very good mathematical libraries. I mean, I know people who disagree. There are people who disagree and love it, but that's, I think,
Have you considered some other mathematical methods for performance?
Well, I would, if I have to use, I will use the TensorFlow and whatever the language TensorFlow provides, right? So I'm not going to consider normally by default. I'm not making the networks. But no, I haven't personally because I'm not making the programs with networks. Cool. I think thanks for listening. And I'm happy I'm here. So if anyone wants to have a question, cool.